So this is the fourth FRQ on the Unit 11 project. Let's get into it. So we're going to need to know a few things. First, charging voltage, this equation. This is actually given to us in it, but it's important to know it. And then also our I of t. This is pretty, you just using Ohm's law, you can figure this out, but see. And then so that'd be charging, and then when it's discharging, you get C of t. And then I of t. And then our time constant. Oh, no, all erased. Okay. Well, we need a clean board anyway. Our time constant, that's RC. And then we should also know capacitance is proportional to A over D. So if area increases, C should increase. And then, yeah. So let's get into it. Draw a schematic diagram of a circuit that can charge the capacitor and may. Sweet. Okay. Well, we're gonna have our battery. It's gonna be here. And then we're gonna have it can charge. So then we're gonna have our switch right here. It can be open or closed. And then let's have a resistor here. And then also we could, okay, and then there'd be a capacitor right here. Oh, a variable capacitor. And then we'll have, and then the voltmeter will be across C, like that. And then our switch 2 could be closed. And could be something like that. So that's my schematic. And then in this scenario, it'd be discharging. Whereas if this was open and that was closed, it'd be charging. Okay, so now we're going to derive this. So we're going to use Kirchhoff's loop rule. That's a physics fact relevant equation. Another one we're going to know. So our VC is going to equal the IR, that resistance, because that's the potential drop. So then our I equals VC over R. And then we know that current is current is also is equal to negative C dVC dt. So that, and then this is how we could set up differential equation. And then we get dVC over VC. And then we're going to integrate and see that ln VC over delta V naught equals negative T over RC. And then from that, we get VC of T V naught e to the negative T over RC. That's the correct equation. Now let's move to C. So draw the best fit line. Well, on a paper, FRQ, it'd be really important to use a ruler, but we don't have that. So try my best. That's, not the greatest, but it'll do. So it'd be you on if you don't have a ruler, use I guess your hand. You could use another pencil, just anything to make it completely straight, and that it goes through this top point and this bottom point, which I didn't do too good a job because I'm on the computer, but those are our 3 points. Using best fit line, get the value for the unknown capacitance C. So our slope is okay, so our slope that equals -1 over RC. So that means our C equals -1 over our slope. And then we can calculate our slope, -1 over our slope. We can calculate slope using, well, if we're using the best fit line, we'd use points on there, but here let's just use data points, so that looks like y2 0. Oops. like around 0.75. And y1 negative 0.1 x1 equals 0.1. So its price overrun, so we're going to get 0.65 over 0.5 negative 0.5. It'll be a negative slope, and then that's going to be 1.3, negative 1.3. And then our R is 1.0 times 10 to the 6. So, and we know C equals negative 1 over negative 1.3 times 10 to the 6. So we're going to get 1.3 times 10 to the negative 6. That's our C. Or, so we can leave it like that, or that's also 1.3 micro. That'd be 10 to the negative 6. Okay, and then let's move on. It should be less steep because you're gonna get a larger area, and that would then mean a larger capacitance. We know areas, and then a larger capacitance would mean a larger RC, and that's smaller slope, because remember, slope is in the denominator. Or well, we had slope equals 1 yeah, C equals 1 over R times slope. So well, our slope is 1 over RC, so greater RC would then make a smaller slope. So, and a smaller slope means less steep. Now, the ideal battery is replaced with a non-ideal battery. Slope. So the time, it's all about would RC change with a non-ideal battery, and it would not. So it would still be the time constants RC, even though it's discharging, so it would not. And then would the vertical intercept in this final experiment change compared to the graph in part C? So with a non-ideal, that would be VC delta V R plus R, and that'd be less than delta V. And we have ln this new over delta V, and that'd be less than 0. So our intercept would be more negative, and that'd mean it would change. And that's it. See you in the next one.